Hello, I'm Ivan Fedyanin. I'm a software architect and a PhD. And today we will learn together merge sort. We cover it in depth. We will check different types of merge sort, different implementations, top-down, bottom-up. We will look at the properties of merge sort. We will compare different implementation. Also, we will show that merge sort is optimal is a number of comparisons. And we'll look into the possible optimizations of merge sort and also its industry implementation. So let's get to it. And before we move to merge sort, we need to understand the basis on which merge sort is built. We need to understand merging procedure. We have two arrays, left one and right one, and they are both sorted, and what we need is to merge them together to make the results in array. To achieve this, we introduce three cursors, one for each array, and initially they are pointing at the beginning of the arrays. And we just compare the elements from first array and second arrays at the cursors. And the smallest one wins, and it's copied to the result array. After that, the cursors are moved. Next, we repeat the same process for next two elements, and now wins the element from the second array, because 3 is less than 5, and we copy over to the result. We repeat this process until we process the whole array. Here is the illustration of all steps required to merge two arrays, and here it's a result array and how it looks on different steps. And there are several conclusions which we could make from this simple algorithm. So let's assume we have two sorted arrays A and B of sizes m and n respectively. Now we should look at number of comparisons, because usually the comparison is the most complex iteration when we consider merging. And we need to understand what is the number of comparisons required to merge those arrays. In the best case, the number of comparisons is just length of minimal array minus 1. It's achieved in the case when all elements of one array are less than elements of another array. And there is the worst case, and in the worst case it's m plus n minus 1, so basically it's size of the resulting array. So the asymptotic runtime complexity in terms of big O is O of m plus n. Memory required for the merging is also m plus n, because we need to have array where we need to place the result. Let's have a look at the implementation. It's code in Kotlin, and the only difference with the example is that usually when we speak about merge sort, it's not optimal to have two separate arrays to merge, and we have one big array, and we just split it logically into several parts. So in reality it's one, but we consider as though it consists of several subarrays. So we need to pass to this function this big array, and also it's the borders of the subarrays which we want to merge. So it's left, mid, and right. So the left array would be from left to mid, and the right subarray would be from mid plus 1 to right. And they are depicted here in different colors. So what we do here? First, we just go through the array from left to right and copy all values to the auxiliary array. Then we set the cursors to the beginnings of the arrays, and then we have a loop until we exhaust all elements either in left or right subarrays, and in that loop we just assign the least value to the resulting array. Once we finish it, we have to deal with the leftover, because if there is still elements in left array which were not processed, we just need to copy them over to the result array. We could potentially do the same for leftovers from right subarray, but it appears that we don't need it, because they are already in the array, so we don't need to copy them again. Now we are ready to dive into the merge sort, and first merge sort belongs to the class of problems which could be solved with the so-called divide and conquer approach, when the big task is split into multiple smaller tasks which are simpler, and they are then joined together to make the common solution. So basically, let's assume we have that array. First, we have divide phase and split this big array into two parts. Then we split each part again to two parts. And last, we split them until we have subarrays of one element. And this is our base case. We see that by definition, one element subarrays are sorted. So we have 8 sorted subarrays here. And now we merge them together using our merge procedure, which we discussed earlier. So we merge one element's array to tuples, then we merge tuples to arrays of 4, and then we merge arrays of 4 to single array of 8. And thus we have our resulting array. Let's look at a specific implementation of merge sort, which is called top-down merge sort. The code is quite simple. We have recursive function which calculates midpoint in order to be able to split the arrays into the left and the right. It sorts them independently and then it merges together the result. The merge complexity is O of n, as we already know. The difference with our generic example would be just an order in which elements are traversed. So top-down, it's recursive, and it will do like a depth first traversal of the tree. We split it on the left side until we get to the base case, and then we merge those two elements together. Then we return and continue with the right side of this subarray until we merge them together, and by this time we have processed the left part of the full subarray. Now we go back to the right part and we do the same with the right part until we have two arrays of 4, and now we just merge them together, and here it is. Here is our sorted array. It's very important to understand the complexity of any algorithm. So let's see what is going on inside of this sort function. So basically we have a recursive invocation of sort function, and we won't consider them here because we will calculate what they do on another level. And in this level we have only merge, which we already know takes O of n operations. And it's represented here. F of n represent here a single invocation of sort function, and the input is a subarray of size n. So there is one node, and we need an operation to process this node. So in total we have on this level n iterations. On second level we have two nodes, but each of them has only n divided by 2 operations. So in the result, if we multiply them together, then anyway on this level we will have n operations. And the same situation is with all other levels. So basically we see that amount of operations on each level is n. It needs to be said that exact amount of operations might be a bit different, but I'm talking about asymptotic approximation. And in this we don't care about constants, and we can consider that we have just n operations on each level. So next question is how many levels do we have? And basically the answer is simple. It's just a binary logarithm of n, and for the purpose of big O we don't care about base of the logarithm. So we can just say that the complexity of the top-down merge sort is O of n logarithm n, and the memory consumption is O of n because we need this temporal array to store our intermediate results. Now let's see another implementation which is called bottom-up merge sort, and it's not recursive. So we have the same array here, and basically we can just consider that it already consists of multiple subarrays of one element each. We don't need some recursive function to split them because it's quite obvious that it consists of elements. And next we will merge them first by pairs. So we merge each pair together into a tuple, then we merge each tuple into an array of 4, and then we merge all of them into the array of 8. And basically the difference between top-down and bottom-up implementations in the order in which we do the merges. In case of top-down, it's like depth first, and in case of bottom-up, it's breadth first. Let's look at the complexity. We have on each level again n iterations to make the merge, because for example here we have merging size 1, which means that we are merging arrays of size 1, and number of subarrays is n. We have very similar situation on each level as we had for top-down merge sort, and again we have logarithm n levels. So basically, again, we can say that runtime complexity is n logarithm n. Memory consumption is also O of n. So from the asymptotic complexity point of view, those two algorithms looks exactly the same. And here is the source code for bottom-up merge sort. Instead of recursion, we have nested loops here. First while loop is going over merging sizes, and on each iteration we multiply merge size by 2. So first we are merging single elements, then we merge pairs, then arrays of 4, and so on. The internal loop just does the merging of all subarrays of the specific merging size. Both top-down and bottom-up merge sort have the same properties. First, it's not in place. It means that it requires additional array of size n for merging. It's not adaptive, means that algorithm doesn't make use of the fact that some elements might be already pre-sorted. And both of the implementations are stable. For the stability, I made this picture because it's not that obvious. So basically, stability is important when we want to keep the relative order of elements with the same keys. For example, here we have this unsorted array, and there are 2 4 here, green one and pink one. If sorting is stable, then after the sorting, they will remain in the same order as they were in the original array. If the sorting is unstable, then they might change places. It's not guaranteed that they will remain on the same relative position. So merge sort is stable. So it's left picture. Let's continue our comparison of the two algorithms. First, let's consider number of array accesses needed to perform the sorting. Both top-down and bottom-up merge sort use the same amount of array accesses. It's 6n logarithm n. As for comparisons, it's a bit more tricky. When n is exactly power of 2, then the number of comparisons are exactly the same for two implementations. However, when n is different from power of 2, then top-down has less comparisons. Here is the table with the results from a white paper, which estimates number of comparisons in best, average, and worst cases for top-down and bottom-up merge sorts. And we see that in average and worst case, top-down has less amount of comparisons, because this term, which is being subtracted from the first one, is bigger in case of top-down merge sort. It's important to note that if we speak about runtime asymptotic complexity, then it's still O of n logarithm n for both of them, because we don't care about constants when we speak in terms of asymptotic complexity. And also we don't care about lesser terms, because, for example, this n logarithm n, it dominates just n. Because of this, in asymptotic sense, those two algorithms are exactly the same. Sorting algorithms are well studied and researched, and there is a proven result that no compare-based sorting algorithm can guarantee to sort n items with fewer than log n factorial compares, and this log n factorial is approximately n logarithm n. Also, we know that the complexity of merge sort is also n logarithm n. It means that merge sort is an asymptotically optimal compare-based sorting algorithm. So here comes a logical question: does it mean that merge sort is an ideal sorting algorithm? Because it's proven that it's not possible to achieve less comparisons than merge sort does. And the answer is no, for several reasons. First, merge sort is not optimal with respect to space usage because it requires just O of n extra space to run the sorting. Also, sometimes average and best case could be more important than the worst case in some applications. Operations other than compares, such as an array accesses, may be important too, and also one can sort certain data without using compares at all. So far, we have reviewed just the basic implementations of the algorithms, and there are numerous optimizations which are possible, and here we will review a few of them. First one is to use insertion sort for small subarrays. It was discovered that merge sort has a lot of overhead for small subarrays, and it's much easier to use some simpler sorting algorithm, for example, insertion sort for small subarrays, and thus we just change our base case from single element subarray to, for example, 15 elements subarrays, which are sorted with insertion sort. It was shown that runtime of merge sort improved by 10 to 15% with this optimization. Next one is just to make a test before merge if the arrays are already in order. Indeed, if all elements are left subarray are already smaller than on all elements of right subarray, then we don't need to merge because they are already sorted. Because they are sorted, it's very easy to check that. We just need to compare two elements together, the last element in the left subarray and the first element in the right subarray. And if we compare and see that the arrays are already sorted, we just skip merging procedure. So in the base case, runtime complexity is dropped to O of n. In the worst case, we will just have n-1 extra comparisons. Why n-1 is depicted in this picture? We need one extra comparisons for each merge. And how many merges do we have? They are counted on this picture. So to sort array of size 8, we need 7 merges. We could extrapolate it, and thus we have n-1 merges and thus n-1 comparisons. The last optimization which we will consider here is eliminating the copy to auxiliary array. In our implementation, on each iteration, we first copy elements from original array to auxiliary array, and then we merge them back into the original array. And we could just swap the roles of the arrays on each pass. So we can first consider this array to be auxiliary and consider result array to be array B. And on other paths, we could just switch terms, and we'll use this array as the main array and this one as auxiliary array. Because on each level we have 6n arrays comparisons, 2 for the copy, 2 for the compares, and 2 for the copy back. Now we don't need the copy step, and we have only 4n array accesses instead of 6n. And thus the amount of array accesses is reduced by third. There are, of course, much more optimization, but they are out of scope. There is another important variation of this algorithm, which is called natural merge sort. The main idea is to somehow reuse the fact that some elements in the array might be already pre-sorted. So we need to develop a function which would find all these naturally sorted subarrays inside of this big subarray. And this function is very simple. It accepts the array as an input parameter, and it returns the array of starts of each sorted sequence and the number of runs, number of those sorted sequences. And then we'll just merge sorted sequences together. And that's it. The code of this natural merge sort is presented here. So first we need to find natural sequences. Then we have those loops. In the inner loop, we go through all identified runs and just merge adjacent arrays together. In the outer loop, we go through the array until there is only one sorted sequence left, which occupies the whole array. There are some trade-offs for this implementation. And first, we need extra O of n of runtime to determine the runs and extra O of n memory to store the runs. Because in the worst case, if there are no natural sequences at all, the amount of the starts would be equal to the amount of elements in the array. But the advantages is that in the best case, the complexity of sorting becomes O of n on pre-sorted arrays. Also, it was researched that in real applications on real data, there are a lot of cases when we have pre-sorted sequences. Therefore, this algorithm is very good for real-world cases. It's worth noting that those trade-offs, they are not significant in terms of big O, because asymptotic runtime complexity is still O of n logarithm n, and space complexity is still O of n because we can drop the constants and not significant parts. So in asymptotic sense, those trade-offs don't exist. The last topic I'd like to cover is Tim sort. Tim is an engineer who researched the merge sort and created algorithm with multiple optimizations. It's based on natural merge sort, which is respecting both ascending and descending natural sequences. It uses insertion sort for the small subsequences and has a lot of other optimizations. And this sorting algorithm is so good that it is widely used in industry. For example, here is the source code of Java, OpenGTK, and we can see that it has this Tim sort. It was used in Java since Java 7 up to current version of Java, which is 23. Here, as usual, I present topics which were not covered in this video, but they are related to the topic. And if you want to have more dimensions in your understanding of this topic, you might want to look at those topics as well. Here are the books and white papers I used. And that's it. Thanks for watching up to this. I hope you have enjoyed this video and it was clear and useful. If you have any questions, don't hesitate to ask me. I will be pleased to answer. And also, if you find this useful, please like this video and subscribe to the channel, because it will help my motivation to create any further videos on this channel. Bye!